Okay, I'm going to make a video now on the energy orbital diagrams. So these are the ones that, like on the test that you had to show what the energy orbital diagram was for the atom that was hybridized. So I'm going to kind of re-explain how to do that. And even though you didn't have to do it on the test, except technically for the one that had 5 or 6 substituents, um, you would benefit greatly from drawing out the original energy orbital diagram for the regular atom and its atomic like ground state when it's just hanging out being a normal atom before it's hybridized, because it really helps look at that, because when it goes to hybridize, he has to take those original orbitals when he was just chilling and hanging out, and he has to take that stuff to mix together to make the new hybrids. So it really helps to kind of look at what we were working with to start with, because you got to look at that before picture and like pull stuff from that before picture to put into your the hybrid, right? Which you put to the new diagram that you're going to make. So I'm going to use carbon as an example, like I always do, because I like using carbon as an example because it's one of the only atoms that can do sp2, and sp3 hybridization. So it's a nice one to kind of use because then I only have to have one before instead of all the after ones. So kind of reviewing from the very first unit we did, you have to be comfortable getting the electron configuration for the atom that's in question here, because in order to draw the correct energy orbital diagram, you need to know its configuration. So there's 2 different ways. I'll kind of quickly review that. There's 2 different ways you could do it. There's one way you can do it using the orbital block diagram, and there's another way to do it by using what some people call the Christmas tree. Nobody's ever called it that before, but it's called the Christmas tree now. There was this way too. So then you'd want to look at the periodic table. If you're going to use this method, you'd look at this and you'd say, okay, carbon has 6 protons, so he has 6 electrons total as well in his ground state because he'd be neutral. And then you'd come over here and say, okay, I have 6 electrons total, and we fill 1s first. And how many electrons can fit in an s? Only 2. Then after 1s fills, we fill 2s. How many electrons can fit in an s? That's 2. So we have to stop here and count. We have 4 electrons already. We only have 2 more left because carbon only has 6. After we fill 2s, then we can come up and fill 2p, but there's only 2 more electrons that we need. So his configuration is 1s2, 2s2, 2p2. If you like using the other way, the orbital block diagram way, which is honestly faster, and this way is actually like foolproof. There's like almost no way to make a mistake on this one. You want to look at your normal periodic table to double check to make sure you know where carbon is. You're like, okay, carbon is up here. He's in period 2, and he's 1. He's 2 guys over. So you'd come here and like, okay, this is where carbon is. He's right there. And then you start at the very top, right? You're going to have to cross the 1s block first. So 1s, and how many things are here? 1, 2. So that corresponds to 1s2. Then you have to cross 2s land. 1, 2 things there, hence 2s2. And now he's 2 steps over in 2p. So we should end with 2p2. He's the second element over in 2p. Right? Every time we walk on the periodic table, we gain a proton, but we also gain an electron. So this is helping us, right? It's the same kind of idea. We had to gain an electron every time we took a step right on the table. So this will help correspond to get that thing there. So this also helps you really quick. Like let's say that you were doing, xenon, right? Xenon is this guy right here, right? Just you can quickly look at it and say, okay, I know for a fact that the electron configuration for xenon, it needs to end in 5. He's going to be 5p6. The last thing I write should be 5p6 because he ends the 5p block and he's going to be completely filled, right? So that kind of helps. Like this one, you can just quickly get a snapshot of what that electron configuration is. But you can use the Christmas tree if you want to as well. But anyways, we want to use this regular configuration to get the energy orbital diagram, because this is just the ground state electron configuration. But we want to write it out in terms of like, right, this is like increasing energy that's on this side here. And you kind of want to think of like this area is for S's, this area is for P's, D's, and F's kind of thing. So we have like one S, and how many subshells are in an S? How many orbitals, excuse me, are in an S subshell? Just one. So you draw one line to represent the one orbital. You have two electrons there, 1, 2. That's 1s. Then we move on to 2s. So I'm going to go higher in energy. 2s is higher in energy. It's further from the nucleus. All right, I'm staying in like this s column here. There's two electrons there. And now the p's are written like slightly over to the right, and there's two electrons there. So I'm going to count where the p's kind of are. P's are higher in energy than s, even though 2s and 2p are the valence shell, right? Those are the valence electrons. Like the p is technically a little bit higher in energy, which is why I'm writing those where they are above the 2s, and there's only two electrons here. All right, and just to double check, right, we need 6 electrons total. We have 6 electrons total in the picture. If you look at the periodic table, carbon is in family 14, so he has 4 valence electrons, and he is in period 2, which means the second energy level is his valence energy level. So this whole space here, his 2s and his 2p, this is his valence shell. So if he goes to hybridize, it's only these guys that are hybridizing. So anytime you go to do the energy orbital diagram for the element that's hybridized, you only do it to the valence shell. So any of the core electrons you leave alone. We learned that in unit 1, right? Core electrons are not involved in bonding, only valence electrons are involved in bonding. So you copy your diagram and you're only changing the valence shell. And you should only be giving electrons in those final hybrid orbitals that are the same number of valence electrons you start with, right? When an atom goes to hybridize and change his orbitals, he's not magically gaining or losing valence electrons. The number of electrons he had is still there. He's just changing the distribution and changing the different orbitals that he's putting them in. But you still need, in this case, if we're doing carbon, you still need the 4 electrons that are originally there. So this is what I call atomic carbon, or this is a carbon in its ground state, right? Its neutral state. This is carbon before he's done anything. This is carbon when he's just hanging out, right? Looking like this. His electron cloud is 1s2, 2s2, 2p2. He's this big crazy mess like this. Just regular carbon hanging out being himself. But let's say that carbon is going to sp hybridize. So this is going to be for sp hybridized carbon. So something that would do that, again, would be something like this, right? This carbon right here and this carbon here, they're both going to do the same hybridization because they're doing the same thing. And I mean, if you watched the last video, we've already had review, but how do I know it's sp hybridization? Carbon has 2 substituents, so I need 2 hybrids. And the only way to get 2 hybrids is if I use 2 of my original atomic orbitals. Remember that cheat? 2 substituents means I need 2 hybrids because I want to get all my substituents at equal energy. So I better put them in hybrids so that they're the same energy, right? 2 substituents, 2 hybrids, which means I need to use 2 of these guys over here. And that's going to correspond to that sp hybridization. I'm going to take an S and I'm going to take a P. I'm going to take a 1s and 1p. That's 2 things. I'm going to mix 2 things to make 2 new hybrid orbitals here. So this is why I said it really helps to draw this out. So first of all, I'm going to keep 1s the same because those are core electrons, so they're not being touched, so they're like the same exact, right, energy as those guys. Here's why I told you guys to draw the original over here, because it really helps you look at, right, we're going to take this guy and turn him into this guy. So sp hybridization literally means I took an S and I took a P, right? So I have to take his S and I have to take 1 P only. I'm going to be taking these 2 guys here, this S and this P, and I'm going to mix them together and then put them in 2 equal piles, right? I am using 2 of these so I can make 2 of these. However many of these I use, that's how many of these I can make, right? My atomic orbitals have to equal the same number of hybrid orbitals or molecular orbitals that I'm making. So I'm going to take an S and a P, and what carbon's really doing, he's like straight up legitly just mixing them. He's mixing their shapes, right? S is spherical. You got the P that are the long, skinny, like dumbbell looking ones. And he's really going to make an average. It's going to be the average shape of an S and a P together. It's going to be the average energy of an S and P together. So an SP hybrid is 50% S, 50% P. It's going to be halfway, right? Between the energies. It's going to be the average, literally halfway between them. To come over here and go 1, 2. Those are my SPs that I just made. I took these two guys, took an S and a P, mixed them together, and made two equal piles, right? And we're lazy, so we just call the new orbitals, this is an SP, and this is an SP. We're naming it after the stuff we used to make it. Like I said in the last video, it's kind of like you took a red and a blue, like red and blue clay, mixed it together, and made two little purple clay balls. Instead of calling it purple, we're just calling it red blue, right? That's what's kind of happening here. This literally means you took an X and a P and mixed it together. So each one of these is an SP. This is an SP, this is an SP. So notice over here, I only used one of those P orbitals. I still have two P orbitals left over in the 2P, so I still have to include those. So if whatever you didn't circle to like mix and bring over, those two circled in green, I mixed them and put them over here. Like they're gone now because they're now over here. I still have these two orbitals that I did not use. So I still got to make sure that I still have those 2P, the two 2P orbitals that are there. And how many valence electrons does carbon have? 4. So now I need to make sure that I'm putting his 4 electrons in here. And where they're going to go is 2 in there and 2 up here. And why is that? Again, let's kind of zoom in on acetylene, or that's like my organic chemistry brain. Ethine is the official IUPAC name for that guy. But here he is right here. Let's just focus on this carbon on the left. So they do the same thing. But he has 2 sigma bonds, and he has 2 pi bonds. Single bonds are always sigma, and because like the first bond any two atoms make is a sigma bond according to the valence bond theory. So sigma, sigma, and 2 pi. So we learned that a sigma bond in the valence bond theory was that if a sigma bond is made when another atom comes and overlaps or crashes into one of your hybrid orbitals. So carbon needs to leave an open spot in his hybrid so that those sigma bonds can actually happen. Because one thing you guys need to remember is carbon is going from this to this before he turns into something like this. If he wants to make this, if he wants to be linear and bond a hydrogen and a carbon, he has to change himself before he can do this. This is kind of showing the before picture for what did carbon have to change into? How did he have to look? Where did he have to put his electrons before he was allowed to do this down here? So his normal, right? He has this dream of doing this, so he has to hybridize himself and do this. Now he's ready to now do this thing down here. So if he needs to make 2 sigma bonds, right? We said that you have to have, right? Something's going to come crash into your hybrid and interact. Like this electron right here that was in that bond, that's this electron right here, right? And he's leaving an open spot for hydrogen to come over and crash into that orbital and donate his electron and make a sigma bond, right? This electron right here, right, is this one right here, right? He's putting one electron in that orbital and he's leaving an open spot, right? He's putting bait there so that something will come in and crash into it and donate an electron there. So if you have 2 sigma bonds, you have to leave 2 open spots in the hybrid orbitals, right? Because you fit 2 electrons in each orbital. If we put 1 in each, right, there's 2 open spots. Pi bonds, we learned, happen with overlap of leftover p orbitals. So this electron here is this electron right here, right? If he wants to make a double bond to something, he better have an electron in a p orbital. And this electron right here, this final one here for the triple bond, That's this one. So he puts one electron in each of his leftover p orbitals so that he can make a double bond and that he can make a triple bond. So this is how he's getting set up and ready to go so that he can do something like this, right? Let's do another type of hybridization here. I'll do a regular atomic carbon again. I'll do these kind of quicker since I already did these. I did the first one a little bit more thoroughly. There's the regular carbon again. Let's say that he's going to go sp2 hybridized. So let's do sp2 hybridized carbon. Right? 1s stays the same. Right? And sp2, right, that would correspond to a trigonal planar electron geometry. So that would be like if carbon wanted to do something like this and have 3 substituents total, right? Trigonal planar electron geometry, that's 3 substituents, which means he needs 3 hybrids, right? Which means we need to take 3 of the original atomic orbitals to do that. So that's going to be the S, if you use that one sheet, right? S, P, 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 all that thing, right? 3, count 3 over, it's going to be sp2. So it literally means, sp2 means I'm going to take an S and 2p and mix them together, right? I took 1, 2, 3. I need to make 3 ones. And sp2 hybrids, right? They're 2/3 P and 1/3 S, right? They're literally 1S and 2P mixed together. So they're going to be a little closer to the P than this one was, right? This was like literally halfway between S and P. This one is going to be about, 2/3 of the way up there. So it's going to be a little bit closer to P, but not quite there. And we made, right, 1, 2, 3 makes 1, 2, 3 sp2s. And what did I not cross off? Oh, look, I still have a p orbital that I did not use. So I still have a 2p orbital up here. Now we have to redistribute carbon's 4 valence electrons, right? We only got 4 valence electrons up here. I got to redistribute the 4 here. And just so we can kind of look at in this thing, because this is what we do sp2. Carbon has 3 sigma bonds and a pi bond. So he needs 3 electrons in his hybrids. He's leaving open spots for those sigma bonds to eventually happen. And he's going to need a double bond too. So he needs to make sure that he has one of his electrons up in the 2p, because that's going to be what gets him a double bond. Because remember, double bonds and triple bonds happen with leftover p orbitals. So if you want a double bond, you better have an electron in a leftover p orbital, right? If you wanted a triple bond, right, you had to have a double and like a triple bond, right? You had to have electrons there in order to do that. And like, if you think about like, why is carbon doing this, right? If carbon is going to have 3 substituents, right? Because he's not going to have one pair. So he's only going to have 3 substituents. He still wants 8 electrons, which means he has to double bond. So he has to leave an electron up here in 2p to get that double bond, or else he's not going to get his octet. Okay, let's do the final type. So we'll have regular atomic carbon, 1s, 2s, 2p. Let's say that it's going sp3 hybridized. So sp3 hybridized carbon. So something like methane. Right? We look at this and say, okay, 4 substituents. I need 4 hybrids, which means I need to use 4 of my original guys over here. So sp3 literally means you take an S and 1, 2, 3 P's. I'm going to take all 4 of those, mix them together, and divide it into 4 equal piles over here. I'm not allowed to touch the 1s because those are core electrons. Nothing happens to those. 1, 2, 3, 4. I'm going to mix them together. They're going to be close to P, but they're a little bit under P because right there, 25% S characteristic. 1, 2, 3, 4. sp3. 4 electrons. 1, 2, 3, 4. Why is it doing that? Because, well, look, carbon has 4 sigma bonds. he needs to leave 4 openings in the hybrids, right? He's kind of baiting somebody to come by and donate an electron there so he can capture it and make a bond and get his octet filled. I'm gonna do I'll do another one with something with lone pairs, like something with like let's say phosphorus or something like that. All right, this is phosphorus' electron configuration. Again, you can get it from the orbital block diagram. You can get it from using the Christmas tree. 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so let's say this is like atomic phosphorus or brown state phosphorus. Okay, let's pretend he goes sp3 hybridized. So maybe he did something like this. Does 3 sigma bonds and has a lone pair left over. 4 substituents though, right? Lone pair counts as a substituent, right? 4 substituents means he needs 4 hybrids, so he needs to take 4 of these guys. I'm only focusing on this part because phosphorus is in period 3. So he has 3 energy levels. So it's the third energy level that's his valence shell. So this 3s2, 3p3, that is his valence shell. He has 5 electrons in the valence shell because he's in family 15. So I have to keep everything the same because the only part that's going to hybridize is this valence shell I circled. So 1s isn't touched, 2s isn't touched, 2p is not touched, but he does sp3 hybridization. So I'm going to come over here and take an s and literally all 3 p's, put them into 4 equal piles because I took 1, 2, 3, 4 of these guys. I better make 4 of these guys. He's a little bit under p right here because he's not quite as high as p. Because p is kind of like right here. So I'm going to go 1, 2, 3, 4. These are my sp3s. And this is where some of you were messing up. There are 5 electrons, 5 valence electrons. So he still has all 5 of his valence electrons. They didn't go away. He changed how his orbitals looked, but he did not change his valence electron number. So follow the Aufbau principle. 1, 2, 3, 4. They each go into their own before they pair up. I'll pair that one up. There's 5 total. Oh, look. There's the lone pair, right? That's going to be in this orbital. And now he's leaving 3 openings for sigma bonds, right? Because he needs to look like this before he can do this. So he's getting set up, right? He's putting his lone pair in one of the orbitals, right? He's literally kind of draw kind of what he's doing. He just kind of morphed into this tetrahedral shape. Let's imagine that looks better than it looks. He put 2 electrons here in his lone pair. He puts an electron in each one of those, and it's kind of like bait because there's like an open spot in each of those places. So something can come in, like hydrogen, and can crash into here. And as soon as that happens, there's going to be a bond that forms, and that electron from hydrogen and this electron here are going to start sharing. So this is kind of what he's doing. He has to turn into this. And once he looks like this, now it's possible for him to do something like this. He's got his lone pair, and he has 3 open spots for something to come in and do a sigma bond to the other 3 orbitals there. I'll do one more example with a 5 or 6 substituented molecule because we don't just go from ground state to the hybridization. Because to have 5 substituents, right? Each substituent has 2 electrons. So if you have 5 substituents, you have at least 10 electrons, right? Like, granted, let's pretend that some of them can be double bonded too. That's why I'm saying minimum of 10, right? If they're all single bonds. If you have 6 substituents, right, we're talking about a minimum of 12 valence electrons once you're bonded. Nothing wants 10 valence electrons. Nothing wants 12 valence electrons. Everything besides hydrogen and helium, oh, I guess lithium and beryllium too, they all just want to have 8 valence electrons. Nobody wants 10, nobody wants 12. So if we're going to force it to do something it doesn't want to do, we have to put energy into the atom and like make it kind of mad and like excite electrons into high energy states so that they're going to be desperate to bond and come back down in energy again. So let's say that we had, we'll do, lose one. Phosphorus pentahydride. 5 subs. I need 5 hybrids. That's going to correspond to sp3d because again, here's that sheet. Right? S, 3 Ps, 5 Ds, 7 Fs. 5 substituents. I need 5 hybrid orbitals, which means I need to take 5 of these original guys. 1, 2, 3, 4, 5. There's that cutoff. What is that? Oh, look, it's sp3d. That's the type of hybridization it's going to have. Here's my regular phosphorus, though, right? Does he have a D? Right? To do sp3d, you need a D subshell. Because what does this mean? This means that you took an S, 3 Ps, and you took a D and mixed all 5 of those together to make your new orbital. But if you look at regular phosphorus here, I don't see a D subshell here, right? So we have to excite electrons into that D subshell to like activate it so we can then use it to then hybridize. So we can't go from regular atomic phosphorus to sp3d hybridized phosphorus because regular phosphorus right now doesn't have any electrons in a D subshell. So we got to make him mad by giving him extra energy. And just to keep, for the sake of time and just so it doesn't get too messy, I would technically have to rewrite all this stuff, right? All of this as the core electrons, right? So I'd be writing 1s2, 2s2, 2p2. So I'm just going to focus on this part right now for brevity. But a 3s, 3p, I know for a fact, right, that I have to have access to 3d or else I'm not going to be able to make sp3d hybridized phosphorus. So phosphorus is able to do this because phosphorus has 3 energy levels, and we get the D subshell once we get to 3 energy levels, right? You have to have at least 3 energy levels. You have to be that big and that many electrons to have access to a D subshell. So phosphorus is able to do this. So that means that if he's sp3d, that's only 1 D orbital we need. So we only need 1 electron up there, right? Nothing likes a D subshell, right? D subshells are unstable. So it's not going to put more electrons in the D than it has to, right? It's like we need at least 1. We're just going to get 1, right? We don't want any more. We don't want nothing else to do with the D subshell. So that means that one of these original 5 electrons have to get promoted up here. And we have to make a decision, well, which one of these electrons do I want to promote? And we have to remember that subshells are the most stable when they're completely filled to capacity. So S would have 2 or P would have 6. Second best option is for them to be half filled. So P with 3 or S with 1. But if you notice right now when he's just hanging out being regular phosphorus, his P subshell is already half filled. And his S has just a 2 here. So I don't want to take one of these because now I'm going to make P unstable, right? And plus, even if I took that, I don't even have a P subshell there anymore. I wouldn't be able to get sp3, but that's besides the point, right? Let's just imagine I could, right? What's better? Do we want P to be unstable? Because D's unstable no matter what, because he's not going to have 5 or 10, right? But I want to keep 3p as stable as possible, so I want to keep him with the 3 he had. So what I'm going to do is I'm going to take one of these S electrons and push it up here. So I literally took this guy right here and I pushed him up to the D subshell. So we put energy into the atom, right? Made that electron really mad. We gave it so much energy, it like got pushed out and went up into that D subshell. So this would be the best possible option for it to do. Now that it's excited, this is excited state phosphorus here. Now it can hybridize sp3d because now it has an S and 3Ps, and it has the D that it needs. Now it can take them and mix it all together to make the new hybrids. Oops, I should be using blue. So this is for SP3D hybridized phosphorus. And I'll just do it in the valence shell to save time. But I took an S, 3Ps, and a D. So I'm going to be higher than the P, right? Because I have a little bit of E mixed in now. So I got to be a little bit higher than where those were. And I have 1, 2, 3, 4, 5 orbitals I'm using. So I'm making 5 of these. 1, 2, 3, 4, 5. SP3D. And down here would be 1s2, 2s2, 2p2, right? Because I didn't touch 4 electrons. I'm just saving time and not writing out all that. And how many valence electrons does phosphorus have? Phosphorus has 5 valence electrons. He's in family 15. He changed how his orbitals look, but he did not magically change the number of valence electrons that he had. So we still have to show all 5 of the electrons here. 1, 2, 3, 4, 5. And that makes the most sense because look what he did. He made 5 sigma bonds. So he needs to leave an opening for 5 things to come bond, like and interact with those hybrid orbitals in order to do that. So anything that has 5 or 6 substituents has to be excited first because nothing wants, right, to throw electrons in a d subshell. That's unstable, right? Nothing wants to do that. Nothing wants to have 5 substituents, right? Because that's a minimum of 10 electrons. Now that he's bonded, once he's done doing this, he has 10 valence electrons total now that he's bonded, right? He started with 5. He only wanted 8. But now he started with 5. Now he has 10, right? He didn't want to do that. He's not going to do that willingly. We have to force him to do that. Same thing with 6 substituents. Nobody wants an sp3d2, right? Nobody wants 2 electrons in a d subshell. Nothing wants 12 electrons once it's bonded. Things just want to have 8 and be done. So we need to force them to do this. And the only way to force something against its will in chemistry is you have to give it the extra energy to like fight against what it's naturally trying to do. And I mean, I should have done a better job in drawing these 2 pictures side by side because when I went to put this on the energy diagram here, because this is energy, I would have put these, right? Like I have S3Ps and a D, so I'm going to be these sp3D here. They're slightly above the 3P, right? Because there's technically a little bit of D mixed in, and D's really high in energy. So when I average all 5 of those out, I'd be a little bit higher than the 3S and the 3P. And this is why we're able to get this crap to form like this. It's because right now, look, like this electron right here, look how high in energy it is. It's pretty high in energy. So, and we gave this atom extra energy. So now it's mad, right? We know that things want to be the lowest energy possible. So now that we threw that electron there, he is desperate to like lower his energy back down. But if he, right, does something like this, all of his electrons now that are in sp3ds, they're technically lower in energy than this electron was here, right? Because again, those sp3ds are going to be like right about here, right on that energy line, right? So they're going to be right here. So he's like, you know what? Once you excite me, I'm going to quickly form bonds because if I form bonds, I'm able to lower the energy of all my electrons and get them all the same energy. And at least they're lower right now than what was going on up here before when I'm like high in energy, right? So overall, he's sitting in a better position with the electrons sitting here. And that's why they're going to do that. So we excite it, we make it mad to get access to those orbitals. So it's going to be desperate enough to bond and like lower it back down and get something like that.